Hey everyone, hope you're having a great break and I'm about to ruin it. Smiley face. I'm going to try to do this lesson on video so that we can catch up and be ready for our final exam without having to cut any more topics. So I'm going to teach you integration number 4, and this was the warm-up that I had to start with that practiced a U-substitution. So hopefully you can see this is a definite integral going from 0 to 1, and I'm going to do a very high-tech move of the video camera to my paper so you can see me do this problem. Here you go. Whoa! Alright, so doing the integral from, I want to do this two ways. If I'm going from 0 to 1 of some stuff that is inside a squared, and then I have x dx on the outside, first thing I notice is that I do have an x, a function x, outside the squared, and that what's inside here has got x stuff with it. So I'm feeling pretty good about doing U-substitution, where I can say 4x squared minus 2 is the inside stuff. Taking the derivative of that, I get 8x dx. I want to isolate just the x stuff, so I will put 1/8 there. And then I am going to do a direct substitution where this is my u, this is my du, and I'm going to osmosis the 1/8 out here. So I have 1/8 u squared du. Notice that I don't put any limits of integration here because 0 and 1 are x numbers. I need those x numbers to go here, but only after I put the x stuff back. So I'm going to leave it blank for now, and that's kind of a foreshadowing to an alternate way to do this problem. Anyhow, I'm going to go ahead and use my power up rule, u squared. Integrating that gets me u cubed over 3. I can't forget that I have this 1/8, and I am integrating that again with my upper and lower limits of integration, but they are x numbers, so right now I'm not going to put them anywhere because I still have my u stuff. So now I'm going to go ahead and put my x stuff back, which is 4x squared minus 2. And now I can go ahead and say, oh yeah, I want to do the second fundamental theorem where my limits of integration are 0 to 1. So doing my substitution, I get 4 minus 2, aka 2, don't forget your cubed, silly, minus 0 minus 2, which is negative 2, also cubed, and this 1 over 24 here, and so I get 1 over 24 times 8. Negative 2 cubed is also negative 8 minus 8, this, so I get 16 over 24, aka 2/3. Now, there's my final answer from evaluating the integral, but remember that what I did back here was do u substitution where I rewrote 4x squared minus 2, identified it as u. I integrated, then went back and put my x stuff back so that I could use the x limits of integration. I don't have to do that though. I can go over here and say, well, you know what, instead of having these x numbers, why don't I leave this as u and just create u numbers here? I have u is x stuff. So I just have to say, well, what is u of my upper limit? And what is u of my lower limit? And I get 2 and negative 2. Not a shock, right? But notice that what that allows me to do from here, I never have to put my x stuff back. So I can just say 1/8, I should say from up here, 1/8 u cubed over 3 evaluated not at 0 and 1, but at 2 and negative 2. So now I just say 1/8, put the 2 in here, 2 cubed over 3 minus second fundamental theorem, put the next u, negative 2 cubed over 3, and I get 1/8 times, shocker, 8 plus 8, and I get 2/3. I better get the same answer, and I'm not going to say that one way was all that quicker than the other, especially in this scenario, but it's nice to know that I have the option of doing it one way or the other way. Sometimes AP will actually force you into this scenario by, I've seen multiple choice problems where they don't actually ask for the answer. They ask for what the integral would look like using U-substitution, and they put in 2 and negative 2 as well as 1 and 0 to make sure you know when you're supposed to have the, if you have U, you have to have U limits. If you have X, you have to have X limits. Alright, that's all for the warm-up. Let's go ahead and go through the rest of the PowerPoint. High tech, moving back to the computer. There you go. Alright. These were some common homework questions from Integration Worksheet 3. And I wanted to highlight these. The answers are already online, but I wanted to highlight them because really there were some rewrites that if you remember your algebra, your basic trig, and later on your log properties, it can really help you before you do calculus to make some of the problems simpler. So for instance, I'm just going to set these ones up, and again you can see the solutions online. Moving back to the paper, that first one that was the integral of cosine x dx over sine squared x, I rewrote that as the integral of sine x to the negative 2 cosine x dx, because again I could see that I have u inside a negative 2 and that I have the derivative of it hanging right out there ready to do u substitution. So integrating u to the negative 2 du becomes a fairly simple operation. The same, though, cannot be said for d theta. Annoying, right, that they use theta? Why not just use x? Sine squared theta. I think about this the same way. I start on like, no doody-doo, no worries. I'm just going to have that as sine theta to the negative 2. There's my inside stuff. D theta, I go u is equal to sine theta, and then I do du cosine theta d theta, and I go to substitute there, and I go to you can't just insert a cosine. You can insert a multiplier by a number, a constant, because you can just osmosis that out. You can't osmosis cosine theta out. You're stuck. What this says to you is, this was a nice thought. You tried U-substitution, but sorry, U-substitution doesn't work. That means that somebody has to come to my rescue. Is it algebra? Is it trig? Who is going to come to my rescue? Dun, 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 dun. Trig. 1 over sine theta squared is the same thing as cosecant squared theta d theta, and shocker, this is on my list of derivatives that I know. Who is the antiderivative of cosecant squared is the same question as saying to you who has a derivative of cosecant squared, and that is cotangent theta plus c, oops, it begins with a c, negatize. So hopefully you can see that from here U-substitution worked because the derivative of my inside stuff, cosine, was floating around. I tried to identify sine in this problem as my inside stuff, but I don't freaking have the derivative of the inside, and I can't just invent it. So, thought about algebra, thought about trig. It was trig that ended up helping me in this situation, and then I just knew the rule for the antiderivative of cosecant squared. The next one, algebra, is going to come to my rescue, because if I looked at that next one, it was secant theta times the quantity secant theta plus tangent theta. And I thought for a minute about making this my inside stuff, but then I thought about the derivatives of each one of these things, and I thought, ew, not right there, by the way. So I said to myself, well, why don't I undo those parentheses? So I got the integral of secant squared theta plus secant theta tangent theta. And the integral of a sum is the sum of the integrals, and the integral of secant squared theta is a formula I've memorized, and the integral of secant theta tangent theta is an integral I've memorized. The integral of secant squared is sure enough tangent. If you really want, plus c. And then the antiderivative of secant theta tangent theta is just secant theta plus some other c. So my final answer would be tangent theta plus secant theta plus c1 and c2. I might as well call that c3. And then, oops, I think I'll just call it c. Yay. The more experience you get doing these and using rewrites, the better you will be. Or the easier you will recognize what to do. All right. This is my power-up formula that I use when I have something x to squared, x to the negative 2, stuff to the negative 2, stuff to the 3, and I know I just add 1 to the exponent and divide by the new power. We had a rule that said that doesn't work when x is equal to negative 1. Boo-hoo. Power down. So, I want to know how to integrate 1 over x, which could also be, of course, 1 over x stuff. Or, if I rewrite that, x to the negative 1, or stuff to the negative 1. Firstly, I think about this graph. That's my old rational function graph. I took Algebra 2 and I paid attention. And I know that I have a continuity issue. And I know that I can't integrate across an asymptote. So there's their asymptote at x equals 0, but everywhere else, this is a rational function, so everywhere else I have continuity. And so if I'm doing an definite integral, as long as I'm not going across that asymptote, I'm good to go. Well, what I want you to do is on your calculator, I want you to type in to y1 1 over x, and then we're going to do second trace 7. And watch the calculator collect area for us. It's a cute little visual. So here is my calculator screen. And there's 1 over x in y1. And then I want you to do second. Oh, let me show you my window. I made my window, my x min go from negative 1 to 5, and my x max 5, my y min's negative 1, and my y max is 2. Then I'm going to do second trace 7. And I want you to choose a lower limit of 1, hit enter, and an upper limit of 1, hit enter, and shocker, you're going to get 0. I want you to repeat that process. Second trace 7. Do not change the lower bound. Keep it 1. but this time go to 2. Enter. And notice the calculator actually draws in the area under the curve from the x-axis up to 1 over x between 1 and 2. Second trace, 7. I'm going to go from 1 again. I'm not going to change the lower limit. And I'm going to go to 3 this time. And I get more area. From my properties of integrals, I should not be surprised that if I do second trace 7, and I start at 1, I'm not going to change that, my lower limit is 1, but I go to 0.1, so dx is negative. My integral is also negative. Now what I did is I went to Stat, Edit, and I filled in the integral values I got from collecting area under 1 over x. I filled in all the values I got. Some positives, 1, 2, 3, 4, and then I went backwards, and I went from 1 to a half, 1 to 0.1, and 1 to 0.001. I'm going to turn my plots on, and I'm going to graph. There's 1 over x. And then if you can see the stat plot, maybe it won't surprise you to learn that those values naturally are ln x. The freaking antiderivative of 1 over x, collecting area under the rational function 1 over x, yields the natural log function. That's crazy. Crazy, I say. Math is awesome, right? Now we do have the issue with continuity, so look at how we've taken care of this. The antiderivative is the natural log of the absolute value of x. And if you remember your definition of absolute value, what does that mean? That means that as long as x is greater than 0, then you take the natural log of that number. But if x is negative, you take the natural log of the opposite of x, therefore taking the natural log of a positive number, which, as you remember again from Algebra 2, because you paid attention, the domain of the natural log function is x is greater than 0. Notice that in this definition, 0 is not included in either one of the pieces of the natural log of the absolute value of x. This needs to go on your list. And what I mean by list is this. Hopefully you have started to keep an antiderivative list. I'll show you mine. I have it over here. My list of derivatives. There was my power up rule. Then I had trig. We did sine. I gave you cosine. I gave you secant squared. I gave you cosecant squared. And then I said secant tangent, cosecant cotangent, and then we stopped. But now you're going to add to your list that you can integrate something to the negative 1. Stuff to the negative 1, x to the negative 1, and you get the natural log of the absolute value of x plus c. That goes on your list. So, if I was to ask you to do these two examples, notice one is indefinite and one is definite. Both of them are take U-substitution, neither one a particularly difficult U-substitution. So the first one is 1 over x plus 3 dx. I don't really need U-substitution since the derivative of my inside stuff is just going to be 1. But I'm going to rewrite that as the integral of x plus 3 quantity to the negative 1 dx. So u is x plus 3, du is just 1 dx. So I can do a direct substitution here, and I get the integral of u to the negative 1 du, or ln, absolute value of u, plus c. Put my x stuff back. Thinking to myself, this is a linear function, x plus 3, with a range that goes from negative infinity to infinity, so I do need my absolute value bars, because there are x's that I can put into this expression, the argument, and get a negative number, take the absolute value of it before I apply the natural log. The next one was a definite integral. X squared plus 1 was in the denominator, so notice I write that to the negative 1, and then I had x dx. U is my inside stuff. Du was 2x dx, getting my x stuff by itself. Allows me now to substitute. I'm not going to put my x bounds up there because I have u stuff. So I have u to the negative 1 du osmosis, the 1/2. Integrating gives me 1/2 ln, absolute value of u. Don't need my plus c because I'm going to evaluate it at my upper and lower limits of integration. And again, at this point, I can either put x back in and use 0 and 1, or put 0 and 1 into my u function and replace it here. So for instance, if I do u of 1, I get 2, and u of 0, I get 1, because 1 squared is usually 1, plus 1 is 2. 0 squared is 0, plus 1 is 1. And then I can fill in these boxes with 2 and 1 because they are u numbers. When I now place in, I get 1/2 times ln of 2 minus ln of 1. But I remember from Algebra 2 that the exponent that turns e into 1 is 0. So my answer is 1/2 ln 2. I do this as a multiple choice question. I'm so happy and proud of myself, and dagger, this answer isn't there. But you know what is? That one. Make sure you know your Algebra 2 properties. They will test you on them, and this is how. Knowing this, I can now get you a formula for tangent. If I rewrite tangent as a quotient, sine x over cosine x, and I assign cosine x in the denominator as a power of 1, bring it up to the numerator with a power of negative 1, and I'm going to make my U-substitution, which means I'm going to assign a u value, and then I'm going to suck up the integral of u. I'm sorry, the derivative of u. Like that. So now I have negative u to the negative 1. So I have negative ln u plus c. Yes, I know I didn't put my absolute value bars in yet, because I'm going to do negative ln cosine x plus c. I put my u stuff back, my x stuff, excuse me. Now watch this handy dandy math. I took the negative 1 multiplier in front of ln and brought it up as an exponent on the argument. But cosine to the negative 1 is 1 over cosine. But guess what 1 over cosine is? Why, that's secant. I put my absolute value bars back. And I'm going to put this on my list. And it really doesn't matter that if you want to call it negative ln cosine x plus c, that's the same thing as the natural log of the absolute value of secant of x. But in most multiple choice answers, you're going to see this version. So make sure you add that to your list. Doing the same thing will get me the antiderivative rule for cotangent, for secant, and for cosecant. When you are worried about things to memorize for this unit test, you better know all these. For the AP exam, these three are at the bottom of my list. They're just not tested as much as the other ones are. I gotta know them, but I'm not that pressed about it. Put these on your list. All right, next up. What function is its own derivative like a phoenix rising from the ashes? E to the x is its own derivative. Therefore, what do you think the antiderivative of e to the x is? Drum roll, please. Da, 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 da. Itself. Plus the vertical shift. Love. Love e. You love it. Probably not going to be surprised to learn that the antiderivative of e to the kx, so e to the 2x, e to the 5x, e to the pi x, is simply e to the kx over k plus c. So the answer to this would be e to the 5x over 5 plus c. I didn't put that answer on there. Now, check this out. E is a number a little bit smaller than 3. 2.7, 18, 28, 18, 28, 45, 90, 45, dot, dot, dot. Its derivative is itself. So if I were to guess the derivative, the antiderivative of 3 to the x was also 3 to the x, you would be close, but not quite. Think back, if you can, to when you took the derivative of 3 to the x. You had to spit out the natural log of 3. Since antiderivatives are doing things backwards, instead of spitting out the natural, multiplying by the natural log of the base, you have to suck up, which means you're dividing by the natural log of the base. So there it is in general form. The antiderivative of a to the x is itself a to the x, but divided by the natural log of the base. Convince yourself that that works for e as well. That has to work here, right? This is just a base. It's just a base of e instead of any number. So if I take this antiderivative and treat e as if it's any number, and it is any number, the antiderivative is a, or e to the x, if my base is e, divided by the natural log of e, but what is the natural log of e? 1. Put this on your list. Now, that's the end of the slideshow, and that's all available on, I made it visible on Edline, on the math groups. But I wanted to do a couple, and so is the homework problem, homework worksheet, integration worksheet number 4. But I want to do a couple of problems with you, and I picked out 3 of them, I think, to do. Number 6, number 23, and number 15, all for different reasons. So I'm going to do number 6 with you first. So again, this is number 6 from integration worksheet number 4. So number 6 is the integral, and it's an indefinite integral, of 2 e to the x cosine e to the x. So I have e to the x. That's not e to the stuff. That's just e to the x. But I have cosine of stuff. That's not just cosine of x. I think this should then be my u. And I'm actually going to be anti-differentiating cosine, which is negative sine. So if I, over here, if I make u equal to e to the x, what is the derivative of u? Well, I love e because it's its own derivative and antiderivative. And I look back over to my integrand. Here is going to be cosine of u, and there's e to the x dx, and this 2 should just osmosis on right out to begin with. So I'm going to put the 2 on the outside. I'm going to write cosine of u, and then du. Integrating that becomes negative 2 sine u plus c. Right? So even though there was a bunch of e to the x's around, I was actually anti-differentiating cosine. I could do that because of the function shoved inside cosine, e to the x, had its derivative as part of the integrand. Now I'm going to do number 15 with you. Number 15 is a definite integral lower limit 0, upper limit 3, and it is a quotient, 2x dx over x squared plus 25.
This is actually x squared minus 25, which I fix on the next page.
I'm going to unquotient it by making this to the first. Bringing it up to the numerator, and then hoping U-substitution works. If that is my u, the derivative of u is 2x dx. Oh, happy day. I'm going to switch pages here. So I'm going to integrate u to the negative 1 du, and remember that, u was x squared minus 25. My lower limit, my upper limit was 3. 3 squared minus 25 is usually negative 16. And my lower limit of 0, 0 squared minus 25 is usually negative 25. So I'm going to put negative 25 and negative 16 here. When I anti-differentiate stuff to the negative 1, I get ln, absolute value of the stuff. I don't need plus c because I'm a definite integral. Negative 25 and negative 16. Now remember, I have absolute value bars, so I'm going to put in negative 16, but it's going to be positive 16. I'm going to put in negative 25, absolute value, and get positive 25. I have no calculator. This is multiple choice. That is what I get, only that's not one of my answers. But that one is. Properties of logs. Gonna get ya if you didn't pay attention in Algebra 2. Last one I'm going to do with you, and then I'm going to leave you alone, is number 23 on integration worksheet number 4. Number 23 is also a definite integral going from 0 to 1 of 1 over 2x. This looks kind of simple. Dx. First I'm going to use some Algebra 2 and bring that thing up to the numerator. Paid attention in Algebra 1 as well. Now this is any number to a function. It's not e. So remember, I have to deal with the natural log of the base. Also, I don't just have x. So technically, I have u-substitution where u is negative x, du is negative 1 dx, when I now write my integral, I have 2 to the u du, but remember du has a negative 1 in front of it, so I'm going to put a negative there. I'm not going to put 0 and 1 because they're not u numbers. I could turn them in to u numbers, but I choose not to because I've done that twice already. So when I anti-differentiate, I'm going to get negative 2 to the u over ln2. With my limits of integration. This is just a constant, I'm going to take this out here, and I'm going to write this as negative 1 over ln2, 2 to the negative x, going to put my x stuff back, which lets me put 0 and 1 here. Following down, negative 1 over ln2, 2 to the negative 1 minus 2 to the 0, 1/2 minus 2 to the 0 is 1. Look at my clever looking 1, which is negative 1 over ln2 times negative 1/2, which is positive 1 over 2 ln2. And just like we've shown before, this is a perfectly legitimate answer, is correct if you're writing it, but in multiple choice, most likely you won't see that. You will see this. ln2 squared, or ln 1 over ln4.